Okay, we start to look at the use of functions. Another example of functions is this factorial program. Now, the definition of a factorial is that factorial is the number multiplied by the number minus 1, the number minus 2, the number minus 3, and so on until you reach 1. In other words, you can compute it by saying if the number is less than or equal to 1, just return 1. Otherwise, return the number times the factorial for n minus 1. Because the factorial for n minus 1 is simply the definition of the remaining products after you've multiplied by n. So factorial n is n times the definition of factorial for n minus 1. So it's a natural recursive definition. Now, there are more efficient ways of computing this, but this is one way of defining it. So here we've got a function which calls itself, but it calls itself on a different argument. And this is valid. You can have this kind of recursive definition here, but that's only valid if you know that you're going to terminate. Now, in this case, we do have a termination condition, so that when the number becomes small enough, as soon as it's 1 or less, then we can finish. We can return 1. Otherwise, we're going to compute fact again, but with a smaller number. So the end result of that is that we compute this product. As I say, there are more efficient ways of computing that product, but this is an illustration to show that you can do recursion like this, function calling itself. Now, the main program then can use that function in the same way that we used the previous example to determine whether a number was negative, 0 or positive. You can do the same thing here. Do a bounded loop for numbers 1 up to 14, compute the factorial of that number, and print it out again, remembering to convert the number here and here to a string to print it. And factorial is written with an exclamation mark. Let's try that. Now, I've actually changed this program to compute a bit further the number of factorials, but the first few are the same. 2 times 1 is 2, 3 times 2 times 1 is 6, 4 times 3 times 2 times 1 is 24, and so on. The numbers start to grow more and more rapidly. Obviously, the factorial of 10 is 10 times the factorial of 9, and so on. So the numbers become very large quite quickly, and this is the actual version that's being executed. It's the same as on the slide, except that I'm going up to 50. Now you can go even further. You can go up to, say, 100. Now this is going to compute some very large numbers, but it's going to take some appreciable time, because at the point where you're computing factorial 100, this function is going to be computed itself 100 times. It's going to be invoked 100 times. You're going to start off with factorial 100, then factorial 99, factorial 98, factorial 97, and so on, just to compute factorial 100. Let's see what happens if I do that. We end up with a very large number here, unimaginably large number for factorial 99, but there's no limit in principle to the numbers you can compute using Python. It's unlikely you'd ever use this kind of number, but it can be used. Large factorials can be useful in cryptography, combinatorial analysis, and so on. Okay, so that's recursion and calling functions within another function. Now, another program design example would be to design a game, like a lottery game. So the problem would be to do a lottery with 3 numbers in a range 1 up to 30 and allowing the user to guess 5 guesses. So the program generates some numbers, is the idea, generates some random numbers in this range 1 to 30, and you ask the user to guess those and you limit them to 5 guesses. Making that a bit more concrete, that would involve generating 3 random integers in the range 1 to 30, asking the user for 5 guesses, counting and displaying the correct guesses. You could also check if there are duplicate guesses, so you wouldn't want to allow a user to have 2 guesses that are the same. It wouldn't make sense for them to do so, because if they're both right, then you wouldn't want to count it as 2 correct guesses. And if they're both wrong, then there's no point in guessing the wrong number twice. So you want to exclude guesses that are duplicates. Now in Python we need to use an existing package like we use the math package. We can use a package called random which generates random numbers for us. And we need a function called sample from this random package to do that. Okay, what does this amount to? Well, we import the random package to generate random numbers, and we use this random sample function to generate 3 numbers randomly in the range 1 to 30. And this is now a list of 3 numbers. It's not a single number, but it's a variable that holds a list of numbers. And this is also our first example of a list. The correct counts the number of correct guesses, and then asking the user for guesses is this loop. That loop allows 5 guesses, 1, 2, 3, 4, 5. It executes 5 times, asks the user for a guess, converts that to an integer. If the guess is in the number that was randomly generated and obviously is hidden from the user, then the guess is declared as correct and we increment the correct number. Otherwise we say sorry, wrong guess. So this doesn't do any checking of duplicate guesses at this point. That's a little bit more complicated coding that's needed, but it does count the number of guesses that are correct and finally prints them out. Okay, let's see this running. Now I've actually changed this program a bit so that we can actually see what random numbers were generated, and so in this sense it's a completely pointless game because the correct answer is printed out, but that's just for testing purposes. You would need to see what the guesses are for testing your program, so that you can see that if I get a correct guess, then it's correctly declared as correct, but if I put an incorrect number, then I get an incorrect. And likewise here, and another one, 27, so I guess 2 correct. And you can run some other test cases. Each time you run it, you should get a different set of randomly generated numbers, as you can see. And again, I'm getting 1 correct. And you could try with all 3. So someone is very fortunate and they get 3 correct. And this has also got error checking for duplicate guesses. So in the version that is running, I've again got the same code you saw already, but now I'm printing out the balls. If I want to hide that, I can comment out that statement. Guesses now are kept in a list by themselves, and the empty list is denoted like this. So our variable guesses is a list variable, but initially it's empty. And again, we do this loop of asking the user for guesses. Now here the logic is a little bit complicated, but it should be fairly straightforward to understand. So here we ask for the guess, convert it to an integer. If that was one that was already guessed, then we get the error message that you've already guessed that number, and it's ignored. So you miss your turn. If you guess a number that's you've already used already, you can't have any advantage from that. You miss your turn. Otherwise, the guess is added to the set of guesses, and this is how we add an element to a collection. Now it's going to be accumulating guesses, and the same logic as before, that if I if I correctly guessed, then I get an increment of the correct number, and so on. So this logic is the same. Now I could probably display the guesses at each step. It might be another interesting thing to show. Here, that print is aligned with the body of the loop. So it's outside this conditional statement, but it's inside the loop. It's outside both of these conditional statements, outside this conditional statement and the nested one, purely because of the indentation. It belongs at this level. Okay, let's see what happens when I do that. Now I'm not getting the randomly generated ones displayed to me, so I'm guessing without any clues, and I didn't get any correct. I'm actually printing out the guess here rather than the guesses. Guesses, that's what I wanted to display. Let's try it that way. Again, another 3 numbers randomly generated. I don't know what they are. I've guessed one correctly though. I guessed one incorrectly. And now the guesses are listed in the list variable, which are displayed. And I guessed one correct, and all the guesses are displayed. Try that again with some duplicates. Let's see what happens. If I get a duplicate, it's not counted. And I guessed one correct. Okay, so I don't think I'd win very much on the lottery, but that's a nice example of a game-playing program for implementation in Python. And as you see, list variables, well, they're lists. I hold several objects or several values in this case, and we can refer, in fact, to individual elements as the variable name with 0 for the first, 1 for the second, and 2 for the third. In computer science, we start numbering at 0, not 1. So 23 is the 0th element of the list, and 11 is the first, and 17 is the second. Confusing, but that's how we do it. And they're laid out in a list like this. And we can add elements by the append statement. We can also assign directly in a whole array to a variable by listing them like this. Typically, we can process a list by a loop like this for x in the array, do something. The size of a list is the length, called len array, and we can set the value as I say. Okay, so we've seen already program structure being a list of statements. We've seen different kinds of variables. We've seen all the statements now of Python, and we've seen functions and recursion. In the next part, I will deal briefly with how you use web internet applications in Python.